Okay. Um, all right. Hello, everyone. I'm Andrew Steinacher, and I work on the food and nutrition entities in the Wolfram language. Today, I'm going to be talking a little bit about food and nutrition on some examples of how to use it. As you can see from here, this is the nice little page that we put up to kind of describe what we have and some neat examples to go with it that I'll go over shortly to try and kind of highlight what we have there. Um, in this little paragraph that's up here, we have thousands of packaged food ingredients. We have a nice way to query through them all, natural language capabilities with them, nice information like physical data, like colors, shapes, dimensions, serving sizes, for all kinds of things there. And so you can do some neat things that way. Um, More detailed, perhaps, we have 150,000 foods almost. We have about 25,000 international foods that come from over 20 countries. About 100,000 packaged foods with computable ingredient lists. Um, we have nutrition content for about 150 nutrients, and there's a lot more than just nutrition. We have barcode capabilities, Lingua L terms, food groups, and a lot of other things to help search through them and query through them and that sorts of things. Um, and as I mentioned earlier, shapes, dimensions, and colors for lots and lots of food types. Um, so I guess the examples that I have here basically fall into three categories in each row. Basically, the top row here is kind of like a trip to the grocery store. So we have, PLU codes, brand names, labeling terms, and packaged foods. Um, in the second row is kind of like nutrition and diet. So like I have a little example here to show off the nutrition content of different foods, how you might look them up and visualize them. Another way to look at foods is in your diet is perhaps based on the color alone. Since we have color information, you can sort of go on a color-based diet if you'd like. And there's some nice ways to visualize things there. Um, there's also some nice dietary guidelines that we have for different ages, and so you kind of can visualize the time series of what dietary intake you should have for different ages and that sort of thing. Um, and lastly, there's a neat little example to kind of see nutrition in the periodic table of elements, which I think is kind of a neat way to view and visualize nutrition rather than just nutrition labels and that sort of thing. And lastly, I have a row on cooking and classification terms. So in cooking, sometimes it's nice to know ingredient substitutions, which we have quite a few of those, and there's some nice things we can see there. We can also visualize on compare cooking times of various foods. And then there's a neat example on building a word cloud for different food groups, which we'll look into. Some neat image processing work to be done there. And then lastly, there's an example on the Lingua L food thesaurus um, uh, for international foods, which we might get into towards the end here. I guess to start with, though, before we get too much further, I'd like to point out that it can be a little confusing because you're going to be seeing some yellow boxes and things like that, but I figure it might be a good time to get into some of that stuff. I had mentioned the nutrition, or I'm sorry, the natural language input, which you can do by using control equals. And so if we put in, say, France, for example, this here creates a little yellow box if we accept that. And if you hold your mouse over it, you can see that it's actually entity country France, and which you can also see with input form, for example. So all these yellow boxes are actually expressions written out. So don't be afraid of the yellow boxes. They're really there for ease of copy and paste, for example. But you can get to them that way. If you highlight them, you can do, I think it's Control Shift I or Command Shift I on a Mac, and you can get out the input form of the expression very easily there without too much trouble. So I think even if we like change this to Germany, for example, I think this will let us evaluate that to a different yellow box, for example. In food, however, since we have so many entities for foods, we also have a different thing called implicit entities, which instead of having a string in the second argument, we also have a list of rules there. For example, like if I look up red delicious apple, for example. This here produces a different kind of yellow box that has more stuff in it, and that's because on the inside, if we do input form, for example, you can see here that there's a list of rules in the second argument, which sort of implicitly tells us how to find the foods. So for example, if I do this, you can see there's an entity property, goes to, and then constraints on the apple, the added food types, and so on to be able to search through foods that way. So that's kind of a rough introduction to what you might be seeing further down the line here. Um, so in order to dive in first, why don't we take a look at PLU codes? So we have PLU codes as a relatively new thing in the language, which we have these as entities too. These are just simple numbers that you find at grocery stores, for example. I'll show you the example over here too. Basically, just by evaluating these things, we have properties on categories, commodities, varieties, and those sorts of things, including size information as well. And the nice thing about these is that you can look up the information on the barcodes that you actually find in grocery stores. If you've ever seen these stickers on produce, for example, it's very easy to do, which I'll go ahead and copy over this example here if I can, because I have to click here first. So this is just the image here, and we can use barcode recognize to pull out, to read what the barcode says there, and then we can just yank out the information using string take to pull out what the actual PLU is. In this case, it's 4053. And from there, we can use that to be able to create a data set of information with those. So for example, here, I've just grabbed a handful of information about it. One of the neat things about PLUs is that they also specify the size in a few different ways, one of which is using the diameter. They also do it in terms of count in a certain size box and that sort of thing. But you can see this is aligned to our foods, with the food type being lemon being the food type, and the some individual foods that it's aligned to from there. And of course, this picture only has also has the number written on it, but this one does not. And you can see the barcode recognize still pulls out that it's 4011, and we can use some implicit entity syntax to be able to pull that out. In this case, it's C4011. You should be able to get that there without too much trouble. So you can pull out the nutrition label, which is a little ugly because I'm zoomed in here. So yeah, so that's more or less it for PLU codes. We can zoom forward to the next example here for brand names, for example. So if you go to the grocery store, you see a lot of branded foods for various things, and it's kind of hard to compare them. So with some Wolfram language code, it's not too hard to be able to actually analyze them and do some deeper things. So for example, here's just a list of food entities, nothing special there, just a couple different things. And with a simple entity value call, you can pull out the foods for each of the brands and get the result as an association. So for example, if we look up the one for this brand, you can see we get a list of foods that come out. From there, you can find out how many are in each brand, so you can kind of see the rough distribution of what we have for those. The nice thing that we also have with them is images, so we can just pull that out with the image property. And from there, you can see that the result doesn't look too bad here. You can see what the images look like that way. Here I've just picked a random one from each of the lists of foods just for demonstration purposes. So we can find the ingredients. That's another nice property that we have for each of the foods for the brands. And then doing some aggregation here, we can actually see how many are in each one. And so there's quite a few more for French's, it looks like, than some of the other ones. And if we drop these into feature space plot, which is a sort of like a machine learning and neural network way of being able to figure out where things are aligned, you can actually see that some of the sodas are actually together, some of the pastas are together, some of the candy bars are together, and sort of some of the mustards are kind of together that way, which is kind of a neat way to look at it. Of course, another way to do it is also to use a little plot here, so you can kind of see in 3D space, 3D nutrient space, where the different things run, and there's not a ton of code to be able to pull that off, which is pretty nice there. So moving on forward, there's also a lot of terms that are on packaged foods. Reduced fat, non-fat, no sugar added, sugarless, sweetened, sugar-free. These are all kind of confusing to work with, so we can analyze some of those without too much trouble. By just writing a little bit of code with box whisker chart, we can actually write some code to produce a little chart here to be able to see what the terms are and kind of the error bars on them. So you can kind of see that, high fat and full fat are much higher in, say, calories than, say, non-fat and low fat. Although some of these have much more bigger variations, probably due to the kinds of foods that they're used with, but still kind of neat to look at. We can also see a similar one for sugar labels, for example, where sweetened is definitely on average more than, say, no sugar added or unsweetened, for example. And another way to kind of visualize these is to look at them using a bubble chart. So you can kind of see here roughly where things are there. It kind of provides a neat, easy way to look at things that way. Another thing tying in with the ingredients that we saw earlier, um, this one's kind of a bigger example, so I'll show it here. Basically, we have 100,000 packaged foods, and we have ingredients for those as well. So, for example, if you want to find foods that have the ingredients has lemon powder as an ingredient, we can find that list of foods without too much trouble using this implicit entity lookup system. From there, we can find this is really useful, say, if you have a dietary restriction. So, like if you're a vegetarian, for example, refried beans can be tricky to find vegetarian ones because sometimes, even if they're not listed as vegetarian, they'll have lard as an ingredient. So, in this case, it's nice to be able to uh, find foods without that by using contains none, which isn't too hard. And so, if we write a little function to be able to pull out all of the common ingredient pairings for each of them, we can actually find out which ingredients are paired the most. And then we can do this on a per brand basis to kind of see which ones stick together the most, which kind of makes for a neat way to look at things. Of course, you can go a lot further. So if we only look at the USDA foods, branded foods database, we have about 67,000 of those. And if we find all of the pairs for them, we can also find the most common pairs from there. And in which case here, salt and water is the most common, salt and sugar is next most common, sugar and water, citric acid and salt, folic acid and riboflavin, and that sort of thing from there. The neat thing too is that we don't have to just have raw numbers like that. We can actually visualize this or create it into an actual network or graph of ingredients and how they're paired together. So if you do this, it turns out that it's a very large graph. There are about 5,000 vertices and about 700,000 edges. So it's a rather large graph object. What's neat though is that since it is so big, it's surprisingly connected, which we can do using connected GraphQL. So it's very easy to find that. We can also use other graph functionality like Graph Center to be able to find the ingredients that are paired with the most ingredients. So you can see salt, water, and sugar, very common as we saw earlier, among with several other things. And we can also find common pairings using the PageRank centrality, which we can do using our built-in function for that. And if we just grab the top 10 or so, we still see salt, water, sugar, and so on. But it's sort of a different metric to be able to pull that off. And since we can't look at the whole graph because it would be much too big without doing some paring down of it, an easy way to pare it down is to only look at a specific neighborhood. In this case, we look at only things around licorice root, for example. And in this case, it trims it down. Still, there's about 5,000 edges, so it's a little big and a little hairy, but you can also visualize it in 3D to kind of see. And in a different one, you can actually style the graph out a little bit more to see. So there's a lot of common things and also a lot of far away things from there. Here I've used opacity on the edges to kind of be able to see things. So it's sort of a neat and different way to visualize the ingredients and their structure that way. Let's see, moving forward though, Let's see. 1 second here. So if we move a little further forward, we can look at the nutrition content for different foods, for example. And so I guess I'll scroll over here a little bit to make for a little more room. One thing we can do is given some foods, so in this case here, if we look at raw foods that have the most vitamin C content and we pull out their image and their vitamin C content, which you can see here, we can actually find images for those foods that are high in vitamin C. And we can visualize the results with an image collage. So without too much trouble, we can just run some code here and get a nice little image collage. Now, in order to style this, it would be nice if we could pull out the dominant colors for each of the images, which allows us to just pick out the most common colors, the big main colors from each image for each food. And the nice thing about this is that we can use it to kind of curate a color. So I'm going to save us some time and show the final results of picking the ideal color for each one. But notice there's only a handful to really look at. And once you actually align them with the image, it's actually fairly easy to get to that point. And going a little further, we can actually take this, if this will run. It seems that I've got a little bit of technical difficulty here. If we take those colors, we can actually create a bar chart out of this without too much trouble. So here I've just looked at their vitamin C on a per gram basis. And then with some styling rules, we can actually make a nice bar chart to kind of compare them in vitamin C and iron, for example. So you can kind of see that acerola is very high in vitamin C, but broccoli in comparison is not quite as much. Same thing with iron. If we do the same sort of thing and hand curate a list of those foods as well, see that goose liver is very high, but beans are not quite so much there. So going a little bit further forward, 1 second here. So getting into diets, as I mentioned earlier, sort of a weird diet that people probably don't do too much is doing things based on color. Maybe if you only do green, perhaps, but I could imagine a diet like that. But perhaps another way to look at it is to do different colors. So since we have common colors for many foods, for example, here, if we just pull out the common outside color for all food types, for example, we can wind up with a lot of those. And with a little bit of work, we can also group the colors, group the foods by the colors, just using a little group by here. And I think I can do, can take a few of these just to kind of show what these are. If we take up to, we'll say 3 on each one. You can see that some green foods include abayuka agave, some violet foods like acai berries, for example. Those sorts of things, to kind of see things there. Let's see here. So then if we take all of these color entities, which are color sets, so fuzzy colors in some sense, if we pull out their typical color values for each one, we actually get actual RGB color objects for each one, as you can kind of see there. From there, if we take a look at our color diet here, we can make a data set that kind of shows how many are in each one, and the actual color that corresponds to it, which is nice. And another nice thing to do would be to look at the calorie distributions for each one. In this case here, I'm just going over this data set that we had earlier and making a little calorie distribution here. And so once we've gathered that information, we can make a little box whisker chart, which allows us to show the colors and their calorie distribution. So you can kind of see there's a lot of error, there's a lot more noise on some of these But for the most part, it looks like this color is, a little more than others. Yellow is kind of high, green is pretty low in terms of calories, comparatively speaking, which is sort of neat. So if you were planning to do a diet based on color alone, you may not do so well with green unless you're really trying to reduce your calorie intake, perhaps. Um, Lastly, I'll show a little bit here that you can actually visualize these in 3D space. So here I think I can pretty quickly get this one going as well um, without too much trouble here. So with that, the nice thing is that now you can sort of 3D look at it and then move things around that way. If I can actually get it to load here, and just take a moment. But the nice thing here is then we can drag it around and actually visualize things that way without too much trouble here. Taking a little longer than I thought. In the meantime, while that's downloading, we can jump to the next page here, which would be to visualize dietary guidelines for different ages. Um, yeah, here we go. So you can kind of see that we have this nice 3D image that we can move around and take a look that way and kind of investigate and see that several colors are all pretty close together on the low end of things, but some of them are higher in, say, carbs. And like for blue foods tend to be higher in carbs, it looks like, than the others. And there's quite a few less blue foods than, say, green or brown and those sorts of colors. So that's kind of interesting. Um, Another thing that we can do is visualize the dietary guidelines for different ages. So we have nutrients as entity types, as an entity type. And so one of the properties we have is the daily value bin, which allows you to see what the daily value is at a particular age. And so it produces this nice little table made of piecewise and stuff. And if you plug in a quantity at a particular age, it will give back the amount that you're supposed to have for the daily value. And of course, we have the same thing for other types of DRIs, like the tolerable upper intake level. Um, and so if with a little bit of code, you can draw out a little plot for them, as you can see here. So this is zinc, for example, and this is vitamin B12. There's several different ones: the daily value, the adequate intake, the estimated average requirement, and the RDA, recommended daily allowance, and the upper limit, or tolerable upper limit as it's called. So you can kind of see over time what these look like, which is interesting. And so you can zoom in on specific times if you change the options around and actually zoom in and see that not all of these apply for all ages, and some of them are pretty close together, and they kind of move around as you go on. So it's kind of a neat, easy way to check where you should be or where you shouldn't exceed, for example, like the upper limit, for example. Going a little further, this is a really neat one to look at too, is the trying to visualize nutrition in the periodic table of elements, which is kind of a non-common way, not a common way to do it. So if we start with just a little periodic table blueprint, which I've kind of iconized away here, you can see that basically all we have is just a list of, it's really an association of the element symbol and then the coordinates where the box should go. So there's nothing really too fancy there. Um, and so with a little bit of work, all we have to do is call graphics on that just right, and we can pull out that information and visualize it really easy just to verify that that's what it is. And with a little bit of code, we can make a periodic table value plot, so to speak, kind of like GeoRegion value plot, but instead for the periodic table. And so if we feed in specific nutrients or specific elements that we want to put a number with, that's what it would be. So you can kind of see that they light up and are colored according to the values that are given. So you may wonder, wouldn't that be neat to hook that up to foods? Well, in order to get there, the first thing we'll need to do is find a way to go from a food property to the actual elements that are there. So if I do a little bit of code here, we can pull out all of the food properties that look like relative star content. So that's all of the gram per gram properties we have. Then if we strip off the relative and the content, we're left with just the nutrient name. And from there, we can feed that through interpreter chemical, which allows us to align them to chemical entities. From there, we just grab the ones that are entities, so the ones that succeed, and then we can just map molecule over all of them. And the new molecule head in version 12 allows us to have a computational representation of molecules and manipulate things from there. One of the things is pulling out the list of atoms from them. And from there, if you grab that sort of stuff, then we can ultimately wind up with an association where we have, given a property, this is the breakdown of elements for them, which is pretty handy and useful to use here. From there, then it's not too hard to write some more code that just makes an entity value query for those properties we're interested in, get rid of some of the missing ones, and then, do some work there and find the breakdown of the composition from there for each element. So for example, if I put in red delicious apple there, as we saw earlier, it's not too hard to pull that out. Then from there, it's pretty easy to just feed to that function we made earlier that makes a plot on the periodic table. So this is what an apple looks like on the periodic table, basically. A whole lot of hydrogen and several other different elements, which is interesting. If you compare it with beef, for example, we can actually find the difference between them just by subtracting them more or less. And you can visualize the difference also on the periodic table. And so you can see there's vastly more nitrogen and various things over here, but not too much difference in hydrogen, for example, which is sort of interesting between the two. And so even we'll do it again, and we'll take a look at say chicken liver and chicken breast, for example. There's a big difference in some of these as well. And then apples and oranges, as as people tend to want to do. There's not much difference in hydrogen, it seems, but there is in several others, and so it's a much more dramatic sort of roller coaster in some sense, with highs and lows in various places. So yeah. Let's see here. So moving on past that example, I guess the next one is ingredient substitutions. So basically, we have about 2,000 ingredient substitutions in our system in various forms. There's explicit ones like this one here. So for allspice, if you look up the possible ingredient substitutions, you'll get back an association of entity instances, which is how we represent quantities of food. So in here, in this case, it's 5 milliliters of ground allspice. And one of the substitutions is the group of ground cinnamon, ground cloves, and ground nutmeg, for example. And if we, that's kind of hard to see, but if we visualize it, it's not too hard to build a little tool to be able to show what it turns into with images and that sort of thing. Additionally, we also have another property for the ratios so that you can do this for arbitrary quantities, not necessarily the ones that we have in the system. So that way you can put in any amount that you want and multiply these in order to see. So here in this case, it's about 40%, 40%, and 6% of the volume on the left-hand side, which is kind of nice to see there. And lastly, with a little bit more work, we can go further and kind of compare a lot more of these by using food type groups to be able to group them together and see how they're related there, which is kind of a neat visualization tool to go through there. Moving forward a little more, another piece of information we have is cooking times, for example. So there are some different changes that have to be taken into account between different foods. And so we have a property called the approximate cooking time association, which allows you to get an association of the cooking times for each thing. So if we grab just the first one, you can see barley here. If you pressure cook it, it typically takes about 18 to 20 minutes, whereas corn grits, it's 5 or 6 minutes, and that sort of thing from there. If we want to do a similar trick as we did before, we can just use dominant colors to pick out some good colors for fonts, for example. And then with a little bit more work, we can put it into a timeline plot to kind of visualize how long it takes to cook each one's in different methods. Like pressure cooking and simmering, for example, are very different for different amounts of food that way. So going a little further, here's a neat one, which is pretty cool to go through. So I'll kind of show that. Maybe I can do this here because it might be a little more exciting to see this way. Let's see if I can find it. So if we just import the USDA's MyPlate logo, so it's just a simple image. So the USDA has MyPlate, which is basically the 5 basic food groups and their proportions, roughly speaking, from there. And if we look at the style guide that goes along with MyPlate, we can look up the actual colors for them. In this case here, we can specify them just as they're specified in the style guide using some new shorthand for RGB color, where you can just pass in a string and it will parse it and figure out what the actual RGB color objects are, which is kind of nice. I believe that's new in 12 as well. From there, with a little more work, we can pull out the basic food group, the food types for each basic food group, which I won't go into too much trouble there. But from there, now that we know the colors in the original image, so the green goes with vegetables, the red goes with the fruits, and so on. With a little bit of work, we can write some code here to do some image processing on that image to detect where each color is, where we can use colors near to be able to detect that. So for the dairy, we can see is over here. For the grains is on this side, the vegetables in the bottom left, fruit in the bottom right, on that sort of thing. All this is done just by using color detect and colors near. I believe colors near is new in 12. Then we binarize the image so it's just black and white, and then we flip it around so that it works the way we want. And we can select out parts that don't contain other parts. Again, flip the colors back, and then we get rid of anything that's smaller than a certain size, and it keeps things nice and clean. From there, it's not too hard to be able to create word clouds for each of these food types for each basic food group for each one. And one of the nice functionalities of word cloud is that once you pass in the information to it with another argument, you can put in a mask, or basically where you want the word cloud to be. In this case, if we want the vegetables to only live in that chunk, this is what the mask would look like. Finally, you can combine all of these together. Oops. You can combine all of them together since they all have white backgrounds. We can just use image multiply. And if we rasterize them all at the same size first, then when you combine them together, you can wind up with a bunch of word clouds together that look kind of reminiscent to the same shape as the original MyPlate logo, which is pretty cool to kind of see from there. So you can see that most commonly is fruit and juice, vegetables, beef, wheat, milk, those sorts of things from there. So it's kind of a fun way to sort of revisit the MyPlate logo with some actual data and information that way, and do just with some simple image processing right out of the box, which is pretty cool. Going a little further is, I believe, our final example for the day, which is the Lengua L food thesaurus, which if I can scroll here for a minute. The Lengua L food thesaurus, oops, let's see if I can get rid of some of this. Oh yeah, this is what I want here. The Lengua L food thesaurus is a set of about 7,000 or so terms for international foods, and they all have these letter codes, like G0012, for example. And it's a hierarchical graph, basically, of these terms. And so you can kind of see here under cooking method, for example, there's several of them. Cooked in steam, for example, steamed without pressure, griddled, popped, toasted, various things that way. Some are very detailed, small amounts of liquid boiled in large amount of liquid. Those sorts of things are pretty detailed in that way. The nice thing about it is that since it is international, it is translated into multiple languages. So with this little bit of code here, basically I can pull out all of the languages using the languages property, and then basically map over all those things, association map rather, and see what the translation is in different languages without too much trouble. So if we translate this one term, you can see these are many languages and many translations for it. Some of the other nice things is if we have a specific food that is tagged with LanguaL terms, you can see which ones are added. Now, compilers, as they're called, are people who are trained in LanguaL and classify foods regularly and very precisely. And so you can see here some of the terms that they are, this one is tagged up with, for example. If we go a little further, we can actually look at, where different terms come from. So for example, here are the number of foods of each one. So this one here is tubers, for example. And if we find out how many are in each country, you can see there's quite a few in Sweden, for example, at least in our data. And from there, it's not too hard to plot with GeoRegion value plot as an example. It shouldn't take too long in a second here. And so you can see most of them are over here, some in the US. As you can imagine, US and Europe, there's a big geographic distance between them. So maybe if we limit ourselves to only, to limit ourselves not in the US or Canada, to kind of focus on Europe, we can build a different plot that does the same sort of thing. In this case here, we can look at different kinds of cheese, for example, basically all cheeses by the time you actually look at these terms, basically cured, uncured, and processed. That's most cheeses, for the most part there. And so you can kind of see where these things are and how they're distributed that way. And on top of that, you can also do a similar thing with cooking terms. So we can see where it's more common to boil in the north, deep fry kind of in the western edge, and then saute is kind of more of a southern thing, it seems, based on this from there. So that's another neat way to kind of query through foods and investigate each part that way. And with that, I think that more or less covers the examples that we have here for food and nutrition. And that pretty much covers it. So thanks for watching, and I guess if there are any questions, I'd love to answer them. I guess I don't see any questions over here, so I think we're good. So thanks.